In this video, I'm going to talk a little bit about tangent vectors. If I'm given a vector r of t, which is equal to f of t I hat plus g of t j hat plus h of t k hat, and it is a smooth curve on some interval, we'll call that interval I, the tangent vector at a given point C on that interval is defined by the first derivative of the vector r evaluated at that point C, as long as the first derivative of my vector r at C is not equal to the zero vector. Now we require this curve to be smooth and that each component be differentiable at all points in the interval, and that the derivative is not the zero vector. Now let's consider a function r of t is equal to t cubed I hat minus 3t squared j hat plus k hat. The first derivative of my vector evaluated at 0 gives me the components 3 times 0 squared, negative 6 times 0, and 0. This reduces to the component 0, 0, 0, or the zero vector. Since all three of my components are 0 when t is 0, it tells me that the tangent line is horizontal at this point. And if a tangent line is horizontal, it indicates the possibility that the curve has a change in direction that is fairly abrupt. This gives me a cusp at that point. This means it's not a smooth curve, which is a requirement for my tangent vector to exist. I want to work some examples using tangent vectors. I want to find the tangent vectors for the following parameterized curves at the specified values of t. The first one is that my vector r of t is equal to the components 2e to the t, e to the minus 3t, and e to the 4t divided by 2, and I want to find the tangent vector at the point t is equal to 0. The second vector is the vector r of t is given by the components 2 times the sine of t, the tangent of t, and the sine of t over 2, and I want to find this tangent vector at the point t is equal to pi over 3. For the first one, I take the derivative of both sides, and on the right side, with the components, I take the derivative of each component. This gives me r prime of t is equal to the components 2e to the t, negative 3e to the negative 3t, and 2e to the 4t. Now I'm going to plug 0 in for t, and I find that r prime at 0 is given by the vector components 2, negative 3, and 2. It's not the zero vector, and so it really is a tangent vector for my curve at t is equal to 0. Let's look at the second one. I again take the derivative of both the left side and the right side, component by component. This gives me r prime of t is equal to 2 cosine t, secant squared of t, and cosine of t over 2 divided by 2. Now I plug in pi over 3, and I find that r prime at pi over 3 is given by the vector components 1, 4, and square root of 3 over 4. There are times when I may only be interested in the direction of the vector and not its magnitude. And in these situations, it is usually simpler to work with unit tangent vectors. So let's let my r vector be given by f of t I hat plus g of t j hat plus h of t k hat, and we will assume it's a smooth parameterized curve over the interval from a to b. The unit tangent vector for a particular value of t is going to be given by the notation capital vector T of little t is equal to r prime of little t divided by the magnitude of r prime of little t. Let's work some examples that involve unit tangent vectors. I want to find the unit tangent vectors for the following parameterized curves at the given values of t, and we're going to assume my curves are smooth curves over the interval that would contain the specific values of t. In the first case, my vector r of t is given by the components 8, negative 2 cosine 2t, and 2 sine 2t. I want to find the unit tangent vector at the point t is equal to pi over 4. First, I take the derivative of the left side and each component on the right side. r prime of t is given by the components 0, 4 sine of 2t, and 4 cosine of 2t. The magnitude of r prime of t is given by the square root of 0 plus 16 sine squared 2t plus 16 cosine squared 2t. This reduces to the square root of 16, or 4. So that my unit tangent vector given by the vector capital T of little t equal to r prime of little t over the magnitude of r prime of little t is given by the components 0, sine of 2t, cosine of 2t. Now I plug pi over 4 in for little t, and my unit tangent vector at t is equal to pi over 4 is given by the components 0, 1, 0. The second vector that I want to find the unit tangent vector for is given by r of t is equal to the components square root of 7 times e to the 2t, 3e to the 2t, and 3e to the 2t. I want to find the unit tangent vector at t is equal to the natural log of 2. My derivative is given by r prime of t is equal to 2 times the square root of 7 e to the 2t, 6e to the 2t, and 6e to the 2t. The magnitude of r prime is given by the square root of 28e to the 4t plus 36e to the 4t plus 36e to the 4t. This reduces to e to the 2t times the square root of 28 plus 36 plus 36, which reduces to 10 times e to the 2t. My unit tangent vector given by capital vector T of little t is the vector r prime of t over the magnitude of r prime of t, and this gives me vector components square root of 7 over 5, 3 over 5, and 3 over 5. You'll notice that all the t's have dropped out, and so this is true for all t, not just t is equal to the natural log of 2. So now you get to try it. Pause the video and find the unit tangent vector for the vector r of t is equal to the components square root of 2t plus 1, sine of pi t, and 4 at t is equal to 4. When you're ready, restart the video to check your understanding. The first thing I'm going to do is take the derivative of r of t. I get r prime of t is equal to the components 1 over the square root of 2t plus 1, 1 over t, and 0. The magnitude of my first derivative of r of t is given by the square root of t plus 1 quantity squared divided by the product of t squared times the quantity 2t plus 1. This becomes t plus 1 over t times the square root of 2t plus 1. The unit tangent vector, capital T of little t, is given by r prime of t over the magnitude of r prime of t. I put my vector for r prime of t over the magnitude of r prime of t. Then I plug in the value 4 for t. I get the components 1 over the square root of 8 plus 1, 1/4, and 0, divided by 4 plus 1 divided by 4 times the square root of 8 plus 1. This reduces to the components in the top of 1/3, 1/4, and 0 over 5/12, and I get a unit tangent vector with components 4/5, 3/5, and 0. This is how we can work with tangent vectors and the unit tangent vector. Let me know if you have any questions.